Today we are studying reaction kinetics. So the rate at which a chemical reaction process, like you can say that the branch of chemistry, kinetics, the branch of chemistry that deals with the rate of chemical reactions, mechanism of the chemical reaction, and the factors which affect the mechanism of a chemical reaction. Okay. We find information about the speed at which reaction occurs. Kinetics also sheds light on the reaction mechanism, how the reaction occurs. Okay. Note important point here that reaction kinetics tells the fact of change in condition of irreversible reactions. But we studied in our previous lecture, Lee-Chatelier principle tells the fact of change in condition of reversible reactions. Okay. So this is for irreversible. Okay. Reaction rates, we study rate laws, integrated rate laws, half-life, Arrhenius equation, and mechanisms. Okay, factors that affect reaction rate. Okay, here we have first concentration of reactants. What effect of reactants on the reaction? As the concentration of the reactants increase, so does the likelihood that reactant molecules will collide. The rate of reactions depends upon the nature of reacting substances. You can say that the chemical reactivity of substances controlled by the electronic arrangements in their outermost orbitals. For fast reactions, some fast reactions include you can say neutralization. Neutralization is a fast reaction. Okay, and also moderate reactions are like alkali metals, alkaline earth metals mostly show, you can say, moderate reactions, but alkali metals are more reactive than alkaline earth metals. Okay. Slow reactions such as fermentations, organic reactions, they are like or oxidation, reduction reaction, they are comparably slow speed reactions. Okay. The effect of concentration we were studying. Effect of concentration, basically it is these reactions are affected like due to collisions, like the concentration of reactant increases, so the collisions of reactant molecules will increase. The frequency with which molecules collide depends upon their concentrations, and that affects the rate of the reaction. Okay. So when for solutions, the rate of reaction is directly proportional to concentration of reactant. Okay, for gases, but for you can say for solutions, it depends upon, for solutions rate depends upon concentration of reactant. But for gases, rate of reaction depends upon pressure inside the vessel. Gas molecules are colliding with the walls of the container in which they are packed, so the rate of reaction mostly depends upon pressure inside the vessel. Okay. Next is temperature. At higher temperature, reactant molecules have more kinetic energy, move faster, and collide more often with greater energy. The rate of reaction is directly proportional. Collision frequency is more, temperature is more. So these three are related directly. Okay. For a collision to be effective, at this case, the molecule must possess the activation energy. They must be properly orientated. Okay. Most of the molecules will possess average energies. Like the curve at higher temperatures will be flattened. Like you can say, I will draw you a graph here. Okay, you can see graph. Okay, this is temperature T1. This is T1, and this is T2. Okay, T2. Okay, you can see here in the diagram that as temperature increases, the number of molecules in this fraction increases. Here we have kinetic energy on this side, and here we have fraction of molecules. Okay, fraction of molecules. Okay, you can see in the diagram that at higher temperature, that is T2, the curve is flattened. Okay, the curve is flattened. Okay, it shows that the molecules having higher energies have increased, and those with lesser energies have decreased. Okay, so the number of active collision increases, and hence the rate increases. Okay. Okay, when an important other point, the rate is doubled for every 10 degrees Celsius increase or 10 degrees Kelvin increase in temperature, rate will be doubled. Okay, or you can use the formula as like this: rate is equal to 2 raised to power n. You can use this formula. Okay, where what is n? N is change in temperature divided by 10. You can use this formula to find the rate. Okay. So next is catalyst. Okay, catalyst speeds up reactions by changing mechanism. They lower the activation energy, so the reactions will be faster. Okay, reaction rates. Okay, rates of reaction can be determined by monitoring the change in concentration of either reactants or product as a function of time. Okay, you can see here we have 1 mole of A, 0 mole of B at time 0 seconds, and after 20 seconds we have 0.54 mole of A and 0.46 mole of B, and after 40 seconds we can see that the concentration of reactants is decreasing, gradually decreasing. You can see here 1 mole, 0.54 mole and 0.30 mole here. Okay, the concentration of A is decreasing. Here reaction here, okay, butyl chloride here reacting with water, forming alcohol and HCl. You can see concentration of butyl chloride decreases with time. Okay, or you can draw a graph for this, like concentration. This like, you can say concentration decreases. Okay, and with time product's concentration increases. Okay, you can draw, like we'll draw it again. This is reactants one and this is products one. This is product and this is reactants. Okay, so with time concentration of products will increase, and with time concentration of reactants will decrease. Okay, you can write this formula like rate is equal to concentration divided by change in time. Okay. The average rate of reaction over each interval is change in the concentration divided by change in time. You can see concentration of C4H9 divided by time. So we have concentration 1. This we are calculating from here to here. Okay, so 50 to 0 we will get down our answer. Okay, note that average rate decreases as the reaction proceeds. You can see average rate is decreasing. Okay, average rate decreasing. This is because as the reaction goes forward there are fewer collisions between reactant molecules, because a reactant concentration decreases, as concentration decreases, so there are less molecules which make collisions, and collisions of the reactant molecules will decrease. You can see we plot a graph here between concentration and time. You can see here concentration of reactants is decreasing. The slope of line tangent to the curve at a point is the instantaneous rate at that time. You can use this formula to find out the reaction rate. Okay, reaction slows down with time because the concentration of reactant decreases with time. Reaction rate and stoichiometry. Okay, in this reaction the ratio from butyl chloride to butyl alcohol is 1:1. Thus the rate of disappearance of butyl chloride is same as the rate of appearance of butyl chloride or butyl alcohol. Okay, you can see this is decreasing. Okay, and like for this it will be increasing. At one point they will be equal. What if the ratio is not 1:1? Like you can see here 1 and 2 moles here. Half mole is made from each H2 used. So rate equation will be written like this for this section. This is generalized reaction: A, B, B, small c, capital C, small d, capital D. Okay, we will write like this for reactants. This for reactants and products increase. You can see here is negative sign. This shows that the concentration of reactants is decreasing. Okay, here positive sign, no negative signs. Here you can see no negative signs. because the concentration of product is increases with time as the reaction proceeds. Each reaction has its own equation that gives its rate as a function of reactant. This is called its rate law. To determine the rate law, we measure the rate at different starting concentration. Okay, concentration and rate, compare experiments. Okay, you can see concentration there as when NH4 was to double, the initial rates double. Okay, you can see 0.01 to 0.02, this will be 5.4 to 10.8, and the concentration of NO is constant. Okay, when we double it, the reaction the rate will be doubled, and we like 1.5 times, the rate is 1.5 times. This is like, you can say, first order reaction. Okay, if we compare when this is not constant, like when it is constant, you can see this is constant, and we double it, the reaction is also doubled. So when NO2 concentration, NO2 negative concentration increases, the initial rate doubles. Okay, this is also first order. So rate depends on directly proportional to concentration of NH4, and also so the rate equation will be rate law of the equation like written like this. Okay, rate depends on concentration of NH4 and NO2. A rate law shows the relationship between the reaction rate and the concentration of reactants. For gas phase reactant, use PA instead of A. K is a constant that has specific value for each reaction. The value of K is determined experimentally. Okay, constant is relative where K is unique for each reaction. K changes with temperature. Okay, because this is a constant. Okay, exponents tell the order of the reaction with respect to each reaction. The reaction according to the reaction we discussed previously, the rate will be for first order according to this, and also first order according to this, and overall order will be 2. Okay, because this is 1 and this is 1, so adding all the orders, this will give us 2. Here this integrated rate law, this is not concerned with. Okay, first order. Okay, first order process. Yeah, first order reactions basically, you can say, the reaction in which the molar concentration of one molecule alters as a result of a chemical change. Okay, this is first order reaction. Like rate depends on you can say, for example, rate equals K and concentration of A, and here it will be 1. Okay, consider a process in which methyl acetate converted into this. How do we know this is a first order reaction? How we can find out? How we can know? Okay, so data, we have given data. Thus rate equation will be written like this. Okay, the concentration of this is decreasing with time. When we plot the graph, LC pressure and plot function of time, a straight line results. You can see a straight line is observed. Second order reactions. For second order reactions, we can say the reaction in which the molar concentrations of two reactants alters as a result of change is called second order reaction. Its order will be 2. You can write like rate is K A raised to power 2. Okay, this is some example for second order reaction. Half-life. Okay, like we have like zero order as well. Zero order mostly occurs. Photochemical reactions are usually zero order reactions, and also third order reaction also in with the reactions in which the molar concentration of three reactants molecules alters as a result of a chemical change is called third order reaction. Okay, remember one thing, that you can say that the order will be find out if we have reaction in multi-steps, like not a single step, like 2 steps and 3 steps. The order will be calculated according to the equation, according to that reaction that will be slow. So what is our point? Slow step is our rate determining step. Okay, half-life. Half-life is defined as the time required for one of half of the reactant to be reacted. can see here. Okay, half-life, this is 0.693 divided by K. This is for first order reaction. Okay, first order reaction, you can simply remind this equation. For numerical problems, second order reactions, we use this. Okay, outlines of kinetics. Okay, rate laws, first order, second order, and the second order can be written like this. Okay, all this. Integral rate laws. This is complicated, we will not study this. Half-life, this, and for second order, we will like right will be half-life. We have second order, and like no, not third order. I'm writing for third order here. Third order, it will be 1.5 by K a raised to power 2. Okay, this is for third order. Temperature and rate, generally as the temperature increases, so as the reaction rate. This is because K is temperature dependent, so by increasing the temperature, the rate will increase. The collision model: in a chemical reaction, bonds are broken and new bonds are formed. Molecules only react if they collide with. Okay. Furthermore, molecules must collide with the correct orientation and with enough energy to cause bond breakage and bond formation. This is before collision, and collision. This is after collision. You can see here, two molecules are formed. Activation energy. In other words, there is a minimum amount of energy required for a reaction. This is activation energy. Just as a ball cannot get over a hill, you can see here, without energy, a reaction occur unless the molecule possesses sufficient energy to get over the activation energy barrier. So, an activated complex, you can say, greater the effective collision, greater is the rate of reaction. Rate of reaction is directly proportional to effective collisions. Okay, reaction, you can see reaction coordinates here. Okay, this is activated complex. This is activation energy from here to here, this part. Okay, this part. Okay, and also for effective collision, physical effect is not necessary. Okay, physical effect is not necessary. The collision may be effective or non-effective depending upon the energy of the colliding molecules. Basically, effective collisions like take place when the colliding particles possess certain amount of energy when they approach with proper orientation. Okay. For ineffective, there is no proper orientation. Okay. Effective collision give rise to products. Effective collisions give rise to products, but ineffective collisions does not give rise to products because the reaction is not favorable. In effective collisions, old bonds are broken, and new bonds are formed. But in effective collisions does not result in breakage of bonds and formation of new bonds. So it is like, you can say, opposite of effective collision. Okay. Diagram shows the reactants and products. The high bound point, or this is the transition state. Okay, the species transition state is called activated complex. What is activated complex? Activated complex is an unstable combination of atoms involved in the reactions for which the energy is maximum. It is like short-lived species and decomposes into the products immediately. Okay. When the colliding molecules come close to each other at the time of collision, they slow down, collide, and then fly apart. Okay. When the molecules slow down just before the collision, their kinetic energy decreases and resulting in the increase in their potential energy. Activated complex has high potential energy. Okay. At transition state, kinetic energy is maximum, but potential energy is minimum. Okay. All right. Okay. Yeah. If kinetic energy is less than activation energy, no products, no products. Okay. And if kinetic energy is greater than activation energy, products will be formed. Okay. Temperature defined as a measure of average kinetic energy of the molecule at any temperature. There is a wide distribution of kinetic energies. Okay. This is Boltzmann distribution. Arrhenius equation. Basically, Arrhenius has studied quantitative relationship between temperature, energy of activation, and rate constant. Okay. This K here is specific rate constant. E is the natural logarithm. R is general gas constant. Okay. EA is activation energy, and T is temperature. A is Arrhenius constant. Okay, where A is the frequency factor, a number that represents the likelihood that collision will occur with the proper orientation for reaction, that effective collisions will take place and the products are formed. Okay. As K is dependent variable, it will be written on the y-axis, and temperature is independent, so written as at x-axis. Okay. EA, other factors are, you can say EA, R, and A are constants. Okay. Okay. By after formulating these equations, we will get our equation for this, that will be written like log K log K equals activation energy divided by 2.303 RT plus log A. Okay. Or it can be written as slope can be taken as tan theta. Okay. And equation to find out will be written as slope equals minus EA 2.303 RT. If we are given EA or T, we can find the other one, or given a slope, or find the slope. R is constant here, we know its value is 8.3143 kilojoule joule per mole per Kelvin. Okay. Reaction mechanism. The sequence of events that describe the actual process by which reactants become products is the reaction mechanism. Reactions may occur at all once or at several discrete steps. Each of these processes is known as an elementary reaction or elementary process. Okay. Unimolecular reactions, bimolecular, termolecular. You can see here. First order, second order, third order, and third order reactions. Okay. The molecularity of a process tells how many molecules are involved in the process. The rate law for an elementary step is directly from that step. Multi-step reaction. In multi-step process, one of these steps will be the slower of all the others. The overall reaction cannot occur faster than this slower determining step. The slower step will determine our rate equation. Okay, slow initial step. This is the initial step, so we will write our rate law for this will be R rate is equal to K is equal to NO2 square. Okay, here the necessity for the reaction to occur, but the rate of the reaction does not depend on its concentration. The reaction occurs in two steps. Slow initial step. This two steps. Okay. Yeah, you can see slow step. This is a slow step. The reaction is multi-step, and this is a slow step. So we will take this concentration and write this concentration in our rate equation. Okay. As CO is not involved in rate determining step, it does not appear in the rate law. Fast initial step. The rate law for this reaction is found to be this. This is a fast step. Okay. NO2 Br2 termolecular this is a third order reaction. Okay, this is fast and this is slow, and this will be overall reaction. Okay, the rate of the overall reaction depends on the rate of slow step. This is slow step, so rate equation will be written like this. Okay, so but how can we find this? By using this fast step. Okay, but our rate equation will be written according to this step. Okay, the reactant products of the first step are in equilibrium with each other, therefore rate of forward is equal to rate of reverse reaction. So this will be written like this. Okay, okay. Catalyst increase the rate of reaction by increasing the activation energy of reaction. Catalyst change the mechanism by which the process occurs. It basically increases the reaction rate for both forward and reverse reaction. Catalyzed reactions you can see here, and uncatalyzed reactions you can see here. Okay, how this process. Okay, one way a catalyst can speed up is by holding the reactant together and helping bonds to break and forming new bonds. Okay, enzymes and catalysts used in biological system. A substrate fits into the active site of an enzyme, much like a key fits into a lock. So this is for the today lecture. I hope you enjoyed the lecture. Good luck for the exam. If you have any confusion related to anything, let me know in the comment section.